Okay, so last time we were basically done talking about the different coordinate systems. I just want to say a couple of quick things about spherical coordinates, and that is, I mean, there's some conversion formulas here, you know, for how to convert rectangular coordinates to spherical coordinates. It's done like so, and I just want to show you a handy way to memorize these formulas. Now, you can memorize these formulas. I'll note that I never have my entire life. And I did a second major in physics in which there was just lots and lots of spherical coordinates. I never memorized these formulas because it's so easy to rederive these formulas. And I trust my ability to think better than my ability to remember. Right? So I'm going to show you the thought process there. And the main thing comes down to looking at this triangle right here. Right? This is a right triangle. And one thing that leaps off the page at you is that this angle phi is the same as that angle there. And so notice what we're looking at is a right triangle for which we know one of the angles. So therefore these edges it's going to be sines and cosines. Right? So very straightforward. So for example, this edge here, the z coordinate, clearly rho cosine phi. Right? So, there you go. Z is rho cosine phi. Right. Now, to get the x and y coordinates, it's a slightly different situation. I mean, here's the other leg of the triangle, and that's neither x nor y, but it is something that we've already talked about. That is r. Right? That's the cylindrical coordinate r. So r, clearly, rho sine phi. And r being rho sine phi, notice that allows you to easily write down that x is r cosine theta and y is r sine theta. Right? So that's how you think about it. That's how I like to think about it anyway. And again, in my entire life, throughout my entire undergraduate physics major, lots of spherical coordinates and all sorts of, when you're trying to figure out how electrons move around in the vicinity of an atom, that's spherical. So it's all spherical coordinate stuff. I never memorize those formulas. I just think it through from the picture. Okay. All right, so I wanted to comment on that. Another thing I want to comment on is the various different alternatives that you have for writing down spherical coordinates. And this is not terribly different from an analogous point we made about polar coordinates. So, for example, this point here, you can think of it as being that angle theta, or you could think of it as being that angle theta, right? Go all the way around. And now you're looking in this half plane back here. I didn't give myself enough space, did I? Let me try that again. You're looking in this half plane. Oh, come on. Drawing with the stylus is harder than it looks. So there's the half plane that you get when you think about theta, going sort of an extra half turn around. And in that plane, keeping in mind, there's phi equals 0. There's the direction of positive values of phi, and I'll just make the observation that for this value of theta, you can have phi be negative. And that gets you going in the same, again, right toward that same point. And so you can use a negative value of phi then. And then, rho is whatever that distance is. So this is not the only alternative way to get to that point. It turns out there are actually 4. I mean, obviously there's infinitely many because you can always add 2 pi to any of the angles. But altogether, though, if ignoring the whole 2 pi in business, there's 4 different ways to get to that point. I've only showed you the 2 where rho is positive. There's another 2 ways to get to this point where rho is negative. And so the idea there is, don't think about trying to arrange to go that direction. Figure out what phi and theta would allow you to go the opposite direction along that same line, right? So if you can find phi and theta that correspond to this, you just got to think through the geometry of it and then have rho be negative. And so So there's two ways to do that as well. So grand total 4 different ways to represent this point in spherical coordinates. So think that through. There is a homework exercise on that. It is this one here. All of the ways to represent these points in spherical coordinates. So anyway, answer. There's four different categories, again, each one, plus 2 pi n for any of the angles, and so there's technically infinite. Okay, moving on. Talking about multivariable functions. Y'all have seen functions before. There's a function, right? Yawn. Right? You definitely know what a function is. Now, there's some discussion here. I want you all to read through this on your own about, what is the domain of a function? What is the target of a function? We distinguish between the target and the image of a function. That ends up being important in some cases. But I want to skip straight to what do we mean when we talk about a multivariable function? And here's what I'm talking about. Notice that here we have a function called f, and what we put into this function is an x, a y, and a z. There are 3 separate variables that go into this function. Okay? So 3 input variables. That's a multivariable function. So instead, again, typically we think of a function as, okay, we got a function, a number goes in, and then a number comes out. We are now going to broaden our perspective on what a function is, as a function is a thing where, let me just loosely say, stuff goes in, let's be open-minded about it, and stuff comes out. Again, ambiguous, let's be open-minded about it. So here we have a function with 3 input variables. Now, let's talk about the outputs. What comes out of this function, that is not a number. That is 1, 2 separate numbers that come out. So there are 2 outputs. Excuse me, 3 inputs, 2 outputs for this function. And so, again, different kind of a multivariable function. Okay. I'm going to show you some examples in a couple of minutes. There's one mathematical twist on this that I think is very valuable. It represents a point of view that I'm going to take in this course that not all multivariable calculus courses do. But I want to reinterpret the thing that goes in here. Again, we have this function, and clearly what goes in is 3 numbers. Recall, first day of class, 3 numbers in a particular order. The first one is x, second one's y, third one's z. An ordered list of 3 numbers is a way of characterizing a vector. So rather than think of this as a function where 3 numbers go in, let's think of this as a function where 1 vector in R3 is what goes in. So now we return to the idea of a single thing goes in. It's not a number, it's a vector. So vector in, 3-dimensional vector goes in, and a 2-dimensional vector comes out. And so with this in mind, there's a notation that we use to represent this kind of a function. This is a function from R3 to R2. Because that's what it is, right? This function takes as its input a vector in R3, which, if you want to think about it as 3 coordinates, fine, whatever, 3 real numbers, fine. But it's a vector in R3, and what comes out is a vector in R2. So the domain is R3, the target is R2. Okay. All right, I'm going to show you some examples real quick of multivariable functions. Let me rephrase that. I've already shown you an example, but let me show you some examples of how this is relatable to the real world. So we'll start with this one. This is what I like to call the temperature function. This is extremely relatable. And that is, let's take this room here, right? 3-dimensional room. And notice that at any point, I could put a thermometer right here, and I could measure what the temperature is of the air at exactly that point. Claim that that's a function, because if you give me an input, namely a location, think of that location in various different ways, and that location I could describe by, coordinates, 3 numbers. You can think of that as a vector, right? So a vector goes in. You give me a vector describing location, and what comes out is, after I've measured with my thermometer and I read the gauge, what comes out is, what's the temperature at that location? So it's a function of with 3 input variables and 1 output variable. It's a multivariable function. Okay. Everybody happy with that? No big deal? Highly relatable? Yeah.
What exactly, like, talk about, like, multivariate? What is that? I know, like,
So there's different ways to think about, again, the point of view that I'm pushing is we want to think of what goes in to these functions, namely in this case the location of where we're measuring temperature. I like to think of it as a vector, but you can also alternatively think of it as several variables, right? And so multiple variables being the inputs to the functions. And so the term multivariable is just a way to refer to that there are multiple variables. You could, instead of saying that we're doing multivariable calculus, you could say that we're doing vector calculus. And that's another term that just conventionally, though, it turns out that vector calculus refers to kind of the last third of this course. It's just historical reasons. So I'm going to use the term multivariable calculus, and these are multivariable functions. But yeah, totally. Okay, here's another example. This is what I would like to call the altitude function. And again, highly relatable. You give me a longitude and a latitude, I'll give you an altitude. So 2 numbers come in, 1 number comes out. You give me a longitude and a latitude, I'm going to then go to Google Maps and type in that latitude and longitude, or whichever order. You pick one, but it doesn't matter which order we pick. Enter the latitude and longitude, and it will then tell me what is the altitude of the land there, above the sea level. So, multivariable function. Here's one that's a little weirder. This is a road trip function. So, imagine you get in the car, you go off and you have a nice time on a road trip, right? Well, that activity in that process, for any given time, you have a corresponding location on the map, right? So 1 number goes in, time, and what time is it? And then what comes out is 2 numbers, namely longitude and latitude, describing where you were at that given time. Another function. Okay, and lastly, this is a weird one. You might call this the weather function. I like this example because it's an opportunity for me to talk about different dimensions, I'll say. So here's the idea of my function. If you give me a longitude and a latitude, then I'm going to give you 4 numbers out. So 2 numbers in, longitude and latitude. That once you give me, then I go to weatherchannel.com and I look up the temperature, the barometric pressure, the humidity, and the wind speed at that location. Right? So it's kind of a weird function. There's 2 numbers that go in and then 4 numbers that come out. Strange, but we're just talking about the weather, right? I mean, it's so it's a very unremarkable phenomenon that's being described with a multivariable function. Okay. All right. How do we draw functions? Here's the picture that y'all are familiar with. If you have a single variable function, x is your input variable, right? Now it's common to then choose to call the output variable y and to make it a vertical axis representing y, and this generates for our given function something called the graph. And now y'all are very familiar with graphs. You're probably so familiar with graphs that you don't even realize that there's a process going on here. This is just what you do, right? This is how you represent functions. Some of you might even think, isn't that picture a function? Right? And it's important to realize at this point, and now we're doing multivariable calculus, and the rest of today's lecture is going to have a lot of discussion on this point. So I'm going to elaborate quite a bit on the following point. But you've got to distinguish between a function, which is an algebraic object. It's a thing. It's an algebraic thing, right? Versus pictures that we use to represent it. And it's going to turn out that it's not just this picture. in multivariable calculus. There's actually several different kinds of pictures that we're going to draw to help us understand this algebraic object called a function. So there's the world of the algebra, namely what function are we talking about, and then there's the pictures, the world of geometry. What do we draw geometrically that represents this algebraic thing? So again, in a Calc 1 class, there's only one picture. You got algebra, boom, there's your geometry. You always draw exactly that picture. Not so in Math 212. So now, let me confess, the graph picture is fantastic in a lot of ways. Y'all went to a lot of trouble in a Calc 1 class to learn about various connections between the algebra of the function and the geometry of the graph. So for example, take a point like this one. The algebraic observation that the derivative of the function is less than 0. This is an algebraic statement, right? Derivatives defined algebraically. Less than 0 is an algebraic statement. All algebra here. And we know that has a reliable geometric interpretation, namely the slope of the tangent line is a geometric idea, right? Is negative. Right? So it's downward sloping, you might say. That's a geometric observation. So now you're accustomed to thinking of that as being, well, that's just what the derivative means. It's not. That's how you interpret derivatives in the context of the graph picture. This is the only picture you've ever seen before, so I know it's hard to see why this is an important observation. But that is a peculiarity of the fact that we're looking at it in the graph context. Likewise, second derivative being positive, well, that's an algebraic statement. Concave up, it's curving in a certain way. Well, that's a very geometric statement. Again, that's a peculiarity of the fact that we're looking at graphs. So we will not always be looking at graphs. Here's an example of not a graph that we might use to represent a function. Here, for example, suppose I have a function f from R3 to R2, and you can see that what goes into such a function. A point in R3 is what goes in. A point in R2 is what comes out. I mean, you can think of this as being a literal picture of what the function is doing. The function is taking points out of 3 space. That's the domain. Right? That's what goes into the function. And then once I take that point and put it into the function and do whatever it's supposed to do, then out comes a point in R2. How would I draw a graph of this? That's certainly not a graph. There's no, I'm only, in fact, on this picture representing what's happening to that one point. Right? There's no curve, there's no surface. There's 2 axis systems. This is not a graph. Right? It does turn out, though, that this is a really important way to understand multivariable functions. So we're going to see several more. We'll see how far we get today. Hopefully anyway, we'll see what happens. But be open to the important point that pictures, there's lots of different pictures that we'll use to represent multivariable functions. Okay, before we get to that, I have to talk about equations, multivariable equations. I want to start with just a quick observation about what the difference is between. So the language is very important. Very often students use these 2 words, equation and function, interchangeably. This is you can't do it. You can sort of get by with that in a high school context or something, but it's a real problem in a multivariable calculus context. So, importantly, we just got through talking about functions. Right? Function is people like to think of it as a black box, and stuff goes in and then stuff comes out. So you can think of a function as a process, maybe. That's not what an equation is. An equation is just an algebraic statement. So that involves an equal sign. That's the name equation, right? So there's an equation. Right. This is what's called an algebraic identity. Right? Right? This is always true. This is how algebra works. X plus 1 quantity squared is equal. It expands like this. So it's an equation. It's a statement that's being made with an equal sign about two expressions being equal. In this case, they're always equal. Here's a different equation. This is not an algebraic identity. This is not always true. And yet, we might write something like this down because there are some cases, there are some values of x, maybe that we're interested in for whatever reason, when x squared will equal to 2x. So these are equations. These are equations that are serving different purposes, but neither of these is to be thought of as a function. Right? Take this equation here, for example. What's the function? Is it x squared? X squared is a function that relates to the left side of the equation, but 2x is a different function that's just as importantly involved in this equation. Is it x squared minus 2x? That's a function whose roots would be found with this equation. Right? But anyway, the point is that's an equation. That's not a function. Okay, so make sure to be clear on the difference. Solution sets. It's important to understand that, well, I guess I'll come over here and draw a picture. A solution set is exactly what you think of it is. It is. In fact, you all have seen solution sets a million times. You might not have used the language. There's an equation, x plus y equals 1. The solution set is just the collection of all points that satisfy that equation. So keep in mind a solution, a single solution to that equation, it's a point, so there's an x and a y. Right? A solution is a point whose coordinates x and y, when you plug them into the equation, makes the equation true. Okay. So like I say, old news. I hope this isn't a shocker for anybody. And just introducing the idea of the term solution set. Again, in a high school setting, you might say, well, this equation is that line. Oh, this is a geometric object, right? This is an algebraic statement. They're different things. You might say this is the equation of that line. You might say that the line gives you the solution, the solutions or the solution set to the equation. They're different things. Okay. So what we're going to be interested in now is what do you do when you have an equation that involves 3 variables? And we are going to restrict our attention to 3 variable equations because 4 variable equations is too hard to deal with. The solution set to an equation involving 4 variables, if you think about it, would be a shape in 4 dimensions. And I can't draw shapes in 4 dimensions, neither can you. So we're not going to try, right? But it is really interesting to see all the different things that can present challenges when you have this view as 3 variables in your equations. So what does, for example, the solution set to this equation look like? Now, there's different things you might think. Well, I don't know. It kind of looks like a parabola, sort of. I mean, just algebraically, y'all see how it smacks of parabola. But it also kind of smacks of circle because you see x squared plus y squared. That reminds me of circles. So what does this look like? What kind of a curve is this? Or is it a curve? Maybe it's a different kind of a geometric object? What's going on here? Yeah? Okay. There's various different methods that I'm going to show you for how to answer questions like this. The first one is a method of cross-sections. It's a pretty straightforward process. It is artistically challenging. So you're going to have to practice drawing things in 3 dimensions. Now, what you don't have to get good at is like drawing, like a face in 3 dimensions. That's hard. That's not what we're talking about at all. But you got to be able to draw, kind of geometric objects in 3 dimensions. And we'll talk about that a little bit as we go along. By the way, this time in the course, I regularly get students who tell me, hey, I'm no good at drawing. What do I do? And the answer is, get good at drawing. Now, if you say, okay, but I don't know how to, how do I get better at drawing? Come to my office hours. I'll be happy to show you the tricks that I know. I've, over the years, accumulated a few neato little tricks that I think are handy. So come to my office hours. We'll spend 10, 15 minutes. I'll show you how to draw well. Okay, so here's the idea. We're going to talk about cross-sections of a solution set to some equation like this one. Here's the idea. I want to know points that satisfy that equation. I'm going to try to answer this question by relating it to a different question. Here's the different question. The different question is not what's the collection of all points that satisfy that equation. I don't know how to do that one. But what's the collection of all points that satisfy this pair of equations? So this is the equation I'm interested in, and then notice I've added a second equation, y equals c. I made that up. Arbitrary. It's free country. I can do whatever I want. This is my separate question that I would like to entertain. And what this has to do with the original question, well, I owe you an explanation of why my different question that I pulled out of thin air is at all relevant to the question we're actually interested in. But anyway, nevertheless, free country, I want to consider this question. So, two observations I'll make about it. One is, algebraically, this is actually pretty easy to understand, because if I need for z to equal to x squared plus y squared, and if I also need for y to equal to c, well, then that means that z would have to equal to x squared plus c squared. And let's ask what this is. And this really is, no kidding, that's a parabola. There's only two variables. C is a constant. Let c equals 3, for example. Z is equal to x squared plus 9. Parabola, right? Algebra 2 problem. By the way, I hope y'all remember all your Algebra 2 conic sections. And if you haven't noticed, trig's going to play heavily in this course, so make sure you remember all your trig, all that prerequisite stuff. So yeah, easy to answer this question that I have in blue. Now, the fact that it's easy to answer doesn't mean it's relevant, right? It remains that this is the question we're actually interested in. So now I have to talk to you about how do these two questions relate to each other. And the way they relate is by thinking about what these two things represent geometrically. In green is there's a solution set I'm trying to understand. What is this, y equals c? That's just a plane. That's a vertical plane. This question that I've posed says, I would like to find points that satisfy both of these equations. Now let me say that again geometrically. I would like to find points that are on my mystery shape and that are also on this plane. Now let me say geometric appeal. If I've got a mystery shape and I want to know on this mystery shape what points on that mystery shape are on this plane, I'm taking a cross-section of my mystery shape with this plane. Right? So I'm taking, again, this surface that I don't, this thing that I don't understand, and I'm cutting through it vertically and taking a cross-section. So here's the punchline then. What we found is that we have this mystery shape, but when I set z equal to some constant, I'm sorry, when I set y equal to some constant, so here I've set y equal to whatever that is, I don't know, 1, let's say. When I set y equal to that constant, here's the plane that I'm taking a vertical slice, y equals that constant, and I know that my mystery shape, when I take this slice of it, when I take this cross-section, I get a parabola. And I furthermore know what that parabola looks like. I have an equation for it. The equation of the parabola is z equals x squared plus c squared. So depending on what c is, right, that c how far the parabola is shifted up is c squared. Right, so the further I move to the right, the further my cross-section plane moves to the right, the larger c gets. C squared in green gets larger even faster. It gets faster, it gets larger quadratically. And so the upshift is sort of quadratic in the right shift. That makes sense? Notice that if C is negative, what happens if C is negative? Okay, fine. So if you're taking a cross-section over here, yeah, okay, cool, C is negative, but C squared is still positive, and so it's still an upshift. So we've made some progress in understanding what our object, our solution set, what does it look like? It's a thing that when you take vertical cross-sections of it, you get curves. So right off the bat, I know it's a surface. Right? I kind of stepped on my own language and inadvertently said surface earlier. I didn't want to give away the game. Sorry about that. But anyway, so now we know it's a surface. We also kind of know what this surface looks like. It's made up of a bunch of parabolas. Right? It's parabolas that don't just all sit next to each other. It's parabolas that are kind of shifted up on the sides. The more you go to the side, the more they shift up, and you can kind of sort of get a little bit of a feel for the shape of the surface. Everybody on board? Okay. Now you can play this same game for other variables, right? Arbitrarily, free country, and all that. I just decided, no, I think I'd like to set y equal to a constant. Why? Whatever. I'm in the mood, right? So you could just decide, okay, hey, let's work another related question. Instead of setting y equal to c, and hey, let's see what comes out. We could instead set x equal to c. Whoops, let me highlight. I could set x equal to c, thus giving me that. And now I've got a whole bunch of new curves that I can draw. These are in x cross-sections. Right? We're looking in planes where x is a constant. Again, we get parabolas. Again, we can talk about how much is the vertical shift depending on where the x cross-section is. And we get a bunch of pictures that look kind of like this. And this, apologies, it's really hard to draw these cross-sections. I have a bunch of parabolas, and as you come out, as you move in the x direction, as you come out of the board, out of the screen here, then the parabolas sort of shift up. Let me see if I can kind of sort of draw that a little bit here. As you come out, there's an upward shift to get you to a given parabola. Yeah. Questions? Yes?
When you're drawing it, you set the other variable to 0, so is that what you do deliberately both times?
No, I'm not setting it. I'm not setting x equal to 0. Here I'm setting x equal to a constant, and x could be any constant. So, for example, yeah, go ahead.
What? You're drawing it at y equals 0.
Nope. No, I'm drawing this in this. I've got a plane here. This is the plane x equals c, right? And inside of that plane, I'm drawing. Inside of the plane x equals c, I'm drawing the curve z equals c squared plus y squared. So I'm not setting y equal to 0. I mean, it happens. I mean, side note, the vertex of a parabola happens to be where y equals 0. That's not my choice. That's just how parabolas work. Yeah. Does that make sense?
Yeah.
Cool.
So whenever you have a cross-section that's plane, it's always perpendicular to the variable you're using as a point.
Yep. That's right. That's what if you think about the equations of planes. Right. Go back to section 1.4. I think it was. Right. That's the equation. That's how planes work. Yeah. Totally. X equals a constant is a plane that's perpendicular to the x-axis. Absolutely. Yep. Okay, last choice that I have is I could set z equal to 0. Let's set z equal to a constant. That gives me these equations. Now again, these are familiar. This is a familiar equation. It's not a parabola, this is the equation of a circle. Right, algebra 2, hope y'all remember. By the way, only if C is positive. If C is negative, that's not the equation of anything. It's a swing and a miss if C is negative. Right, so if C is positive, we have a circle. And here's that picture. Right, so when we set Z equal to a positive value, then we get circles. And if we set Z equal to a negative value, then, well, there's nothing down here, right? There are no solutions if C is negative. Okay, so altogether, you use these 3 different pictures that we have. Got 3 different pictures here, and you can kind of piece together what this surface looks like. Right, it's got those cross sections in the y direction, those cross sections in the x direction, those cross sections in the z direction, and it's a bowl. Yeah, everybody happy? There's a bunch of work to go to get that conclusion, but anyway, that's the conclusion. Okay, real quick, I want to show you another example. By the way, this section is full of lots of examples. I couldn't possibly go through all of them. I just want to show you this one because it's a little different, and it's hard to draw. Different equation. I shouldn't do that in yellow. It looks just like my thing. Not the same equation. A little bit different. What does the minus sign do? There's a temptation to underestimate the importance of that minus sign and figure, okay, well then it's just like thing. But I mean, wouldn't it? Maybe it's a bowl that's upside down or something. But no, this is a very, very different thing. And if you just carefully go through and think about, well, what do these various cross sections look like? When you set x equal to a constant, where did I write well, anyway, I didn't write these down. But if you set x equal to a constant, you get an upside down parabola. But if you set y equal to a constant, you just get a right side up parabola that's been shifted down. Right? And then when you set z equal to a constant, you get a hyperbola. So the cross sections of this are pretty weird, and piecing all those together, this is what you end up getting. They commonly call this a saddle, dating the era in which this was first considered. I think if it were discovered in modern times, it would be called a Pringle. Right? So anyway, so you can see there's these parabolas. We have these downward. Well, let's see. Let me do the upward ones first. We have these, in various cross sections perpendicular to the y-axis. We have these upward pointing parabolas that move downward, right? And on the other hand, perpendicular to the perpendicular to the x-axis, when you set x equal to a constant, right, you get these downward parabolas that shift up. And this is really quite artistically challenging, but if you were to think then about a vertical cross section there, what would it look like? I mean, just imagine the Pringle, right? If you were to take a knife and slice horizontally right through a Pringle, it's a good excuse to buy a can of Pringles, by the way. I think you can kind of persuade yourself that you get a hyperbola. Geometrically. All right. Several more examples in here y'all have to read on your own. Okay. Transformation of variables. I'm just going to go right to the picture and actually, no, I do need to write down, one other quick thing. Algebraically, a real quick observation. If you have an equation of 3 variables, I want to think of it like this. I claim you can always do this. Whatever your equation might happen to be, if you have a bunch of junk involving 3 variables equals a bunch more junk involving 3 variables, you can always take whatever is on the right and whip it over to the left and get a great big bunch of junk involving 3 variables equals 0. Right, so you can always rewrite any equation of 3 variables. You can write as some function of 3 variables equals 0. It ends up being convenient. So now I can, having done that, I can refer to my equation as, taking this form. It's just compact, useful. Okay. Okay, so here's the question. Suppose I know what this surface looks like. I've got an equation involving 3 variables, some surface maybe that I've already studied, maybe through cross-sections, whatever, but I already know what the surface looks like. What would happen if I were to go through the equation and everywhere in the equation that I see an x, I just kind of erase and I put x plus 1 in its place? Well, I'm fiddling with the equation. Obviously, the solution set's not the same anymore, but the new solution set that I get by everywhere I see an x, I'm going to replace that with x plus 1. New equation, new solution set. What does the new solution set look like? Okay, so the idea is this. This is what happens when you replace x with x plus 1, right? This is x comma y comma z. This is x plus 1 comma y comma z. You're just adding 1 to the x coordinate. So given an input point x, here's the new output point g of x. Simple formula. Right. Note that pushes in the positive x direction, right, by a distance of 1. So what happens to the solution set, though, it turns out it's exactly the backwards of this. It's exactly the sort of the opposite of what you would expect. And there's a real easy picture for how to decide this. Keep in mind, I've got there's some surface here that I already understand. This is f of x comma y comma z equals 0, and I already know what that is. The solution set to that, let me do this in purple. So that equation is this object. My new thing that I'm looking for the set of solutions. What happens if you take f of x plus 1 comma y comma z equal to 0. That's my new equation that I get by replacing x with x plus 1. And if you just read straight off of what this says I'm looking for points such that when you shove them over in the x direction by 1, I'm looking for points x, y, z, such that when you shove them over by 1 in the x direction, when you push them like this, I want them to satisfy this equation. Namely, I want points that when you shove them in the x direction, land on the surface that I already know. And if you just kind of reverse engineer that and ask, what surface is it that when you push in the positive x direction becomes exactly S? It's the surface that you would get if you took the surface S and pushed it backwards in the negative x direction, like this. Right? So the point here is that we're not doing the plus 1 after we plug into the function. We're doing it before we plug into the function. Right? So you have to it's like the solutions have to anticipate that there's a plus 1 that's going to be added to the x coordinates before you plug into f. Right? You're adding 1 to the x coordinates and then plugging into f and expecting everything to work out. So you're moving it over to get onto the surface that you understand, or said differently, you're taking the surface that you understand and moving it backwards. So that's how that works. I'm going to show you a quick example where you already sort of know that this has to be the way it is. Actually, let me just do it right here. Y'all recall from Algebra 2 class, or whatever they call that these days, that if you have a, let's see here, I'll use green, I guess. If you have a circle centered at C on the x-axis, radius 1, let's say, then the equation of this circle is x minus c squared plus y squared is equal to 1. Right, hope y'all remember your algebra 2. Yeah? If you forgot your algebra 2, you can think of this as a statement about how the distance from that point to that point is equal to 1. This is how you compute that distance, Pythagorean formula. And notice, this opposite phenomenon is happening here. This equation is exactly what I would have gotten if I had started with the unit circle and replaced x with x minus c. Does that move my unit circle in the minus direction? No, it moves it in the plus direction. It moves it in the backwards sort of direction as compared to what you would, as to what that sort of naively suggests. So, very relatable. Okay. So here's a related picture. Actually, let me write down the equations of these things. So here is a sphere. X squared plus y squared plus z squared is equal to 1. That's this sphere here, centered at the origin, radius 1. Not hard to persuade yourself. Think about cross-sections. Right? You can also think about, this points whose distance to the origin is 1. So that's easy to write down. You get this formula. What would happen if I were to replace every x that I saw in this equation with x plus 1? Well, I'm going to get, let's see here. It's now x plus 1 squared plus y squared plus z squared is equal to 1. All right, let's see, back to green. So I've replaced all the x's with x plus 1s. That does not move you in the plus x direction, it moves you in the minus x direction. Which, by the way, you could see by rewriting this blue equation with x minus negative 1 squared plus y squared plus z squared is equal to 1. So it's you can see right there that we're looking at distance from x to negative 1. And that negative 1, it being a reference to that point there. Okay, so nice punchline then. When you fiddle with an equation by replacing one of the variables with some easy little simple variation of it, the solution set does the opposite of what you did to the variable in question. So if you replace x with x plus c, that translates not by plus c, but by minus c. Likewise, if you replace x, let's do y. If you replace y with c times y, some positive constant c times y, it's like we're multiplying the y coordinate by c. You're going to be tempted to say, well, that's going to stretch in the y direction by a factor of c, but it doesn't. It does the exact opposite. It squishes toward the xz plane by a factor of c. Or what I wrote here stretches by a factor of 1 over c. Likewise for reflections. Okay, so I'm going to show you one more example of this. This is just because it's confusing, I think this is definitely worth going through. Let's see, I guess I can zoom back out. That's fine. So suppose I want to understand. Where's my? Here it is. Suppose I want to understand. I'm in yellow again. I want to understand this equation. X squared plus 2y minus 1 quantity squared plus z squared equals 1. So this is an equation of what surface. How am I going to figure out what surface this is? Well, the idea is I'm going to think, okay, well, just conveniently, that equation that I'm trying to understand, I can see there's some easy algebraic transformations that relate it to this equation that I already do understand. Right? X squared plus y squared plus z squared equals 1. Sphere, no problem. And it's not hard to see that I can take this algebra and start fiddling with it in ways that I can write down very easily and turn this equation into this equation. Right? So all you got to do is be careful in your process, right? And each step along the way, think about algebraically what did I do, and geometrically what's the corresponding sort of upside down, reversed, whatever you want to call it, opposite resulting geometric effect. So here's what I'm going to do. I'm going to step 1 in this equation. I'm going to replace every y with y minus 1. Right? Now, just strictly as an algebraic process, don't worry about the picture just yet. Algebraically, though, if I replace all the y's with y minus 1s, then this equation becomes that equation. Right? Again, don't worry about the pictures. And now next, in this equation, if I were to take every y and replace it with 2y, then this becomes that. Now, classical blunder. Everybody does this at least once. So let's get ours out here so you don't do it on a test. There is a temptation to say, but isn't this whole thing kind of y because it came from the y, and shouldn't I replace this whole thing shouldn't I multiply that whole thing by 2? Shouldn't this be 2y minus 2? No, absolutely not. The whole point of this process is once we know what surface is represented by that equation, I no longer have any further need for this. I never heard of that anymore. It's gone. We're not going to think about it anymore. This is what I am working with. That's the equation. I know what the surface is. And the way to turn this into that is to replace the y with the 2y. The minus 1 is an innocent minus. It's sitting there by it, so it's not involved in this substitution here. That takes that replaces y with 2y. You see what I'm talking about there? Okay, so having done this algebraic process, now I just have to ask the question, okay, when I do, for example, that replacement, if I replace y with y minus 1, what happens? Well, we've already talked about this. It's going to be the opposite of what you would sort of think. So you would kind of think this would shift by negative 1 in the y direction. It does the opposite. It shifts by positive 1 in the y direction. So this whole sphere slides over to the right by a distance of 1. Right. Note that makes it tangent to the xz plane at the origin, right there. Right. Okay. Next, my next step is to replace y with 2y. Now again, your knee-jerk reaction is, oh, you're multiplying y by 2. Doesn't that stretch in the y direction? No, it's the opposite. Replacing y with 2y is going to squish in the y direction. So all of the y coordinates have to be cut in half in anticipation of that 2 that it's going to get multiplied by. So all the y coordinates get cut in half, and it's hard to highlight this, but it's like this. Right? It gets squished by a factor of 2. Now be careful with that one. A lot of students mistakenly think that you can kind of squish however you want. Again, if you're thinking about how you would do it with your hands, then you're thinking, well, whenever I squish a balloon, I'm grabbing it on both sides and I push toward the center. And both sides come in that squish. It's not really what we're doing here. Here it's the y coordinates that get divided by 2. So the y coordinate of 0 right there gets divided by 2 and therefore remains 0. This does not shift, this does not squish, and this is sort of shifted away from the origin. It stays at tangent to the origin there. So this point on the right shifts in. The center shifts in by a half. Right? The point on the at the origin doesn't move. Yeah? Everybody happy? Okay. Okay, last thing I want to talk about on equations is rotations. So there's a really nice observation about you get lucky with the algebra sometimes. This does not always work, by the way. This only works in the case of some equations. In fact, that's exactly what. Okay, here we go. This only works for some equations. So there's a great big massive if that starts this whole discussion. So if x and y, so suppose, hypothetically, big if x and y appear in the equation only as part of this expression, square root of x squared plus y squared. That's it. So no extraneous x's. No, oh yeah, there's a cosine y over here. No, nothing like that, right? If x and y appear only as part of the expression square root of x squared plus y squared. So, for example, this could be rewritten in such a way that x and y appear only as part of the expression square root of x squared plus y squared. So, for example, I could rewrite that as square root of x squared plus y squared quantity squared minus z equals 0. No additional e to the x over here. If this happens, big if, but if it happens, then amazing convenience punchline works out. Let me come down to the picture here. Keep in mind that, of course, square root of x squared plus y squared is distance to the z-axis. Right? It's that distance there. So what this is saying is that, if your equation has this feature that x and y do not appear by themselves at all, x and y appear only as part of this one expression, distance to the x-axis, that means that you can decide if a given point is or is not on your surface. Simply, you don't need to know x and y. All you need to know in terms of x and y is whether, what is the value of square root of x squared plus y squared? What is the distance to the z-axis? So, now, of course, you do have to know z. There's no requirements on z. Z can appear sort of however in the equation. But if you know z, and if you know distance to the z-axis, then you know whether or not the point satisfies the equation. So said differently then, if this point satisfies the equation, then this one has to also. These 2 points now, they have different x's, they have different y's, but who cares? The only thing that goes into the equation that we're trying to arbitrate is distance to the z-axis. Well, these 2 points have the same distance to the z-axis. I got them by rotating around, right? So same distance to the z-axis, same z. It's going to be the exact same arithmetic in the equation when you plug in these 2 different points. Different points, but the algebra is going to be identical. So punchline then, if you have one of these equations where x and y appear only as part of this very specific expression representing distance to the z-axis, it's rotationally symmetric around the z-axis. Your surface will be rotationally symmetric around the z-axis, such as what I've drawn here. And that is a tremendously valuable observation to make. When you're trying to draw a picture of something, all these different cross-sections in different directions, and oh my gosh, how do I piece it all together? Knowing that it's rotationally symmetric cuts it down massively. Now, here's how you can capitalize on that. Suppose you know that your surface is rotationally symmetric. Well, a rotationally symmetric surface, if I were to know the cross-section in this 1/2 plane, I don't even need the whole plane. In fact, I need to draw my focus to just this half plane. You'll see why in a minute. If I have a rotationally symmetric surface, and if I know what this blue curve is, what do you get when you take the cross section in this half plane? Well, the fact that it's rotationally symmetric means that I'm just going to take this blue curve, just rotate around the z-axis, drop the mic, and walk away. We're done. I don't have to worry about what happens in this half plane over here. It's just a rotation of that blue curve. Does that make sense to everybody? So that's pretty cool because this half plane is really easy to write down an equation of. That half plane is just where y is equal to 0 and x is greater than 0. I'll say greater than or equal. No big. Y equals 0, x positive. It's really easy to write that down. Now, what's the effect of that? Well, when you do that, keep in mind, I know that in my expression I've got square root of x squared plus y squared is how x's and y's show up. If I take that expression and take advantage of the fact that y is equal to 0, then that turns into square root of x squared, namely absolute value of x. And then when I take advantage of the fact that x is positive, non-negative, I get just x. So it's just so cool how this works out. This little algebraic coincidence of x and y appearing only in a certain form, blah, 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 means it's rotationally symmetric. It means I only have to look in any half plane hinged on the z-axis. Now, I like this one, whatever. You can use a different half plane if you like. But if chosen as I have this half plane, I get these little bits of algebra, which means I get to replace all these ugly radicals with just x. And then I have simple algebra to try to understand that curve, and once I understand that curve, we win. So let me show you a couple of examples of this in action. Let's see, where is my, here it is. Okay, so y'all recall, of course, this equation. Now, we went to great trouble to try to understand. We wrote it z equals x squared plus y squared, same thing. Right? We went to great trouble to try to figure out what in the world that represented there. What's the surface? That's the solution steps of this equation. Cross sections, and well, it's various parabolas shifted in certain ways, and then we look at it over. Okay, now various other parabolas shifted in different ways, and artistic challenges, etc. Now let me show you how easy this is using symmetry. Step 1. X and y appear only in the special form. Ergo, rotationally symmetric around the z-axis. That's nice, right? I'm therefore going to understand what this looks like by, I'm just going to look at the xz plane, specifically the part of the xz plane with x greater than or equal to 0, like we talked about, which turns this equation into, well, let's see here, the xz plane, y is equal to 0, x is positive, which ends up not mattering in this case, but you get x squared minus z equals 0, otherwise known as z equals x squared. Really easy parabola to draw a picture of. Oops. And here's z equals x squared inside of that half plane. That's the cross section in the half plane. Rotate around the z-axis. Bowl. Now I have to draw a bazillion cross sections. Rotational symmetry argument. Look at one easy cross section. Geometric observation. We're done. Isn't that nicer? I'm a big fan. Questions? Anybody? Went kind of fast. Let me show you another example. Let's look at this one here. How would I find the set of solutions to that equation? And this is a nasty one because, oh gosh, it's got a square root in it, and ugh, right? You could do this with cross sections, but it ends up being kind of hairy, and yeah, it's hard. It's really quite hard to do this with cross sections. So, on the other hand, X and Y appear only in that special form. There's no extraneous e to the x's or sine y cubes or anything like that, right? X and Y appear only in that special form. Therefore, this is rotationally symmetric. Therefore, all I have to do is look at any cross-section hinged on the z-axis. Let's see here. Here's my picture. I'm going to look at, as usual, that half plane there. As usual, that means y equals 0, and x is greater than or equal to 0, and therefore square root of x squared plus y squared equals x. Right, now here's where it really matters, by the way. It really matters that x is positive. Right? It really matters that I'm looking only in this half plane. I'm not looking over there in the other half of this plane. I need to only look in the positive part of x, part of this plane. Can't allow x to be negative, because if x was negative, the radical would not equal to x. If x was negative, it would be negative x, not plus x. And so my algebra would work out totally differently, and it would be a problem. So we're going to restrict our attention to the half plane. That's all you need anyway. All you need is a half plane and then make your rotation argument. So square root of x plus y squared is x. That means that all of this right here just turns into x, thus giving me x plus z squared minus 1 equals 0. That's a parabola. It's an easy parabola. It's a parabola that, let's see, I'm going to draw. It's a parabola like that in the xz plane. So it opens in the negative x direction, right? With a vertex at 1 on the x-axis. Now, very importantly, though, keep in mind, cannot emphasize enough, I'm only interested in the part of this that's in that half plane, because I've got to worry about the absolute values and the pluses and minuses. So I can't take the whole thing. I've got to take just the part here where x is positive. I can only draw this conclusion in the positive x portion of that plane. Right, so I can't just draw the rest of that. The rest of this has got nothing to do with this algebra. Is everybody happy with that? Very important. You get the wrong answer if you're not careful with this. You look only in that half plane, and then you say, okay, well, what happens when I take this part of a parabola and rotate around the z-axis and you get a football? That's what the surface looks like. You do not get the weird kind of thing like this that you would have concluded had you included the additional part of the parabola where x is allowed to be negative. That's just wrong, and it's sort of obviously wrong as well. From the look at the equation, there's no way it could possibly work. So you got to be careful. It's just this part, therefore just a football. Okay, several more examples. Let's see here. Again, I'm going to have to ask you to read most of these. This one looks a lot like a sphere, algebraically, at a glance. So, tempting to say, well, it's kind of sphere-like, but again, no, it's absolutely not. Make a rotation argument, though. Notice that x and y appear only in the special form. So this is rotationally symmetric around the z-axis. Pick a half plane. Doesn't really matter what half plane you pick as long as it's hinged on the z-axis. And go through the same argument, and you end up with this picture. So here's your half plane. The curve is a hyperbola. Now again, it's tempting to draw the other half of the hyperbola, and in this case it'd be a victimless crime. You wouldn't get a wrong answer here, but it's not a valid argument. We don't consider the other part. We only consider the part where x is positive. Take this curve, rotate it around the z-axis, and you get this shape here. It's called a hyperboloid. It's called a hyperboloid of one sheet. A different example down here where the minus signs are in different places, you end up with a different hyperbola. And instead of looking at, this hyperbola and taking the part where x is positive, we take this hyperbola. Whoa, missed. Let's try that again. This hyperbola, taking the part where x is positive, rotating around the z-axis, and that makes what they call a hyperboloid of two sheets, which looks like that. All right, there's a bunch of exercises at the end of this section giving you practice in working out these, what happens if you have which kind of surface. By the way, here's a couple of additional theorems. These are the same idea, just applied to rotational symmetry around the x-axis, or rotational symmetry around, for this last one, the y-axis. And you'll notice that the arguments are very similar. Here, in the top one, it's not x and y, it's y and z appearing in a special form. So this is a reference to distance to the x-axis, which means that you have a shape that's rotationally symmetric around the x-axis. Then you look at a cross-section in a plane that's hinged on the x-axis. It's all the same arguments, just the variables playing different roles. So I think it's a wonderful exercise. Just think them through. Try to think through why is this theorem true? What's the picture? And how do you capitalize on that? And it's shameless rip-off, modification of the arguments that we just talked about. Likewise, this one. Okay. So moving along. We've got 4 minutes. We can actually get a lot done here. 2.3, we're going to talk about graphs. Now, we've already talked about graphs a little bit. Basically, I've kind of bad-mouthed graphs a little bit. Right? My complaint with graphs is that it's all students are accustomed to. There's a tendency for students to reflexively think that any picture must be a graph. There's a tendency for students to think about whenever they have a function that the only way to understand it is as a graph. There's both false statements. Right? So that's unfortunate. Nevertheless, as much as over-reliance on graphs is a problem, it remains that graphs are a useful construction, and I'm certainly not opposed to graphs. I've got a pro-graph platform. Just don't rely on graphs, right? Don't just depend on them kind of reflexively, like as if it's by it. So I'll go through Math 212. I'll do everything from a graph point of view. That's not going to work at all. So let me explain exactly what it is that in a Calc 1 class or Algebra 1 class or whatever it is. What is this construction? What is this process by which you form graphs? And here's how it works. You have a single variable function. For example, let's take that one. F of x equals x plus 1. Notice there's only one variable. Thus the name single variable function. The variable is x. You give me an x, I'll plug in, and out comes f of x. There is no y. Right? F of x equals x plus 1. End of story. You do not have to call it y. Does everybody see what I'm talking about here? There's only one variable. What comes out, we just call it f of x. We don't have to give it an additional name. Okay, so having made that observation, there is only one variable as that's part of the function. Part of the graph construction is to say, okay, well, yeah, but I'm going to have a use for taking the value of the function and giving it a name. So as part of the graph construction, we're going to set the output value equal to a new variable. We're going to call it y arbitrarily. You can call it q. I don't care. We're going to call it y. Note that then gives you an equation. It gives you an equation involving now two variables, one of which was the original variable that was part of the definition of a function, right? One was the variable that came with the function. The other one, the second variable, is a variable that you made up that we're choosing to introduce into the situation. Equation of two variables, and now we look at the set of solutions to that equation of two variables. the solution set to that equation. Okay, let me show you the process. For example, here is a here's a function, a single variable function. F of x is 1 minus x. Now, y'all know what the graph looks like because y'all had an Algebra 1 class and y'all have been through this process of, you memorize all the formulas for, mx plus k and all that business, right? But let's slowly and carefully, methodically, go through the graph process. Step 1, take the value of the function, set it equal to a new variable, y. Step 2, look at this equation, y equals 1 minus x, otherwise known as x plus y equals 1, and draw the set of solutions to that equation. And the set of solutions to that equation is this line like that. Okay, so that's a two-step process that associates this line to that function. It is a very specific process. This is called the graph construction. This is not a dictate by law that you must do when you have a function. Not at all. Right? This is a specific, arbitrary choice that sometimes is useful. Okay, and I'm making a big deal out of this because we're going to generalize this specific construction next time to talk about multivariable graphs. Okay, see y'all later.